graphs of sine and cosine functions, I just want to start by sort of reminding you about transformations of functions. If you remember way back in Algebra 2, you might remember the absolute value function, which looked like a v, right? Something like this. You might remember that there were a lot of different transformations that you could apply to this thing. You could do a horizontal shift, left or right. You could do a vertical shift, up or down. You could do stretches. You could do shrinks. And, what you could do with all of that is basically, this thing here is the basic, or sometimes called the parent function, right? And then after you apply a bunch of transformations, like vertical shifts or stretches or whatever, you wind up with a new function whose graph is related to this, but a little bit different. For example, if I put a 2 in front of the absolute value function, and then a minus 3 here, and then a plus 1, if you remember, what this would correspond to is a horizontal shift of 3 units to the right, a vertical stretch by a factor of 2, and a vertical shift up by 1. So parent functions and transformations applied, right? So this thing would look like, let's see, so 3 units to the right, 1 unit up, and because of the vertical stretch, it would be kind of skinnier and taller, something like that. Now, the reason I remind you of that is that just like there's a basic or a parent absolute value function, there is also a basic or parent sine and cosine function. So let's talk about the basic sine and cosine functions. So what do the basic sine and cosine functions look like? What do the parent functions for sine and cosine look like? Here they are right here. So I'll just zoom in and kind of show you. This top one here is the sine function, and the bottom one is the basic cosine function. And as you can see, they're very similar. They're both waves. And I want to emphasize that I've only graphed part of the graph. Of course, it keeps going forever in both directions, and it just keeps bouncing up and down. So I just want to make some observations about these graphs because we have to develop some terminology about how to describe these graphs. The first thing that I want to point out is the bounce numbers. Okay, so both of these graphs bounce between two y values. That would be -1 and +1, right? You can see that the graph bounces between those two numbers, -1, +1, -1, +1, and so on. So we call those the bounce numbers. Midline. The midline is the horizontal line going right through the middle of the graph. With these basic parent functions, the midline is actually the x-axis. Here's the midline right here. As you can see, it cuts right through the middle of the graph. So that is the midline. Then we have the amplitude. So what is the amplitude? The amplitude can be described in a few different ways. You can describe it as the distance between the midline and the top of the wave. That distance right there is the amplitude. If you look, that distance going from 0 to 1, that amplitude is 1 right there. You could also see it this way. That is also 1, so that's the amplitude. Alternatively, you could say that the amplitude is 1/2 the height of a full wave. What I mean by that is if you sort of look at this entire wave all the way up and all the way down, the whole height of that wave would actually be 2, and half of that is 1, which is what the amplitude is. So for the basic sine and cosine functions, the amplitude is 1. Next we come to the period. So the period is how long it takes for the graph to complete a full cycle. As you'll notice, the graph repeats over and over again. And, I would say, for example, if you're thinking that the graph starts right here, looking at the sine function, what does one full cycle look like? Well, let's see. It goes all the way up, all the way down, and then at this point, the graph repeats, right? So this is one full cycle right here. This portion that I've outlined right here, that's a full cycle. And the period is just how long that cycle is. How long does it take to repeat? You can see that measured in radians, it takes 2 pi units to repeat. We often imagine that the horizontal axis is time, So we're sort of asking, like, how long does it take to repeat? Well, 2 pi units. Yeah, so for the basic parent sine and cosine functions, the period is 2 pi. Angular frequency is something that we care a little bit less about. Generally speaking, technically, it's the number of cycles the graph completes in an interval of length 2 pi. So let's think about that. If we look, for example, at the cosine function, here is an interval of length 2 pi. So that right there is an interval of length 2 pi, and we can ask how many full cycles does the graph complete? Well, it looks like it completes actually just 1 full cycle, because as you can see, this thing right here, starting at the top all the way down, coming back up, that's a full cycle. So the basic sine and cosine graphs have an angular frequency of 1, because they complete 1 full cycle every 2 pi units. The reason I say we don't care much about angular frequency is that if you think about it closely, angular frequency and period are giving you essentially the same information. They're kind of telling you how quickly the graph oscillates. They give you the same information, and if you know one, then you know the other. They're actually related by a formula that I'll give you in just a moment. Typically, it is much easier to think about and work with the period, which of course is the length of a full cycle. Okay, so let's just quickly go over those vocabulary words again, which describe these two graphs. We have the bounce numbers, which are the y values that the graph bounces between. We have the midline, which is the horizontal line that goes through the middle of the graph. We have the amplitude, which is this distance right here, just 1 full height of the wave, or if you like, the distance between the midline and a peak or trough of the graph. We have the period, which is the length of 1 full cycle, how long it takes to complete 1 full cycle. Now, those vocabulary words all describe and refer to the basic sine and cosine functions. In a moment, what we're going to do is we're going to take a look at transformed sine and cosine functions, right? We're going to take a look at, just like we have the absolute value function with a bunch of transformations, we're going to take a look at sine and cosine with a bunch of transformations applied. And basically what happens is when you start applying transformations to sine and cosine by like applying horizontal shifts and vertical stretches and shrinks and all these different things, what happens is all of these things change. Okay, the bounce numbers for a transformed sine or cosine function in general will not be negative and positive 1, but some other numbers. The midline, for a transformed sine and cosine function will not just be the x-axis, but some other horizontal line. The amplitude for a transformed sine and cosine function will not be 1, as it is for the basic parent function, but something else. So all of these things change, okay, when you begin to transform the function. Before we take a look at the transformed sine and cosine function, see how each of these things changes when we begin doing horizontal shifts and stretches and all of that, I just want to point out the difference between the sine and cosine graphs because they are very similar. So it's important to recognize what's different about them. Really what I want you to notice is that the beginning of the sine graph at x equals 0 starts in the middle of a wave. Do you see that this is like the middle of the wave? It's not at the top, it's not at the bottom, it's right in the middle. Okay, so that's characteristic of a sine function. On the other hand, with cosine, the graph starts at a peak, right? It starts right at the top. So that is sort of a key way of distinguishing the two graphs. Sine function begins in the middle of a wave, cosine begins at the top, okay? Okay, so let's now talk about the generalized sine and cosine functions. So here I have sort of a general template, right, of the sine and cosine functions. As you can see, this thing is still a sine function, except I've got all this other stuff that's been thrown into the mix. I've got a number out front, A. I've got this other number, which is a Greek letter. It looks like a W, but it's technically an omega. We've got a B, we've got an M, and basically each one of these little things is like a knob that you can adjust, and adjusting the knob changes the graph, okay? And what we really need to do is understand how each of these letters, the A, the omega, the B, the M, we have to understand how each of these letters affects the graph. And in particular, we have to understand how changing each of those letters affects all of the things that we just talked about, the bounce numbers, the midline, the amplitude, the period, and all of that other stuff. So it's pretty straightforward. First of all, what does A do for you? So what is A talking about? You might remember that a number multiplying out front in the function is some kind of a vertical stretch. A determines the amplitude. Okay, so the amplitude, which if you remember is like this distance right here from the midline to the peak, that's the amplitude. The amplitude is given by the absolute value of A, this number right here. And it's important to notice that it's the absolute value because A can be a negative number, like this could be -3, but the amplitude is always positive because it measures the distance, right? It's the distance from the midline to the peak, okay? So that number A determines the amplitude. Omega is the angular frequency. That's how many full cycles that the graph completes in an interval of 2 pi. As I mentioned, angular frequency we won't really work with very much. It's a little hard to imagine. Instead, we'll work with the period. So really, the important thing that omega tells you is the period, okay? And here's the formula. P is equal to 2 pi over omega. This says that the period of the function, that's how long it takes to complete a full cycle, is equal to 2 pi divided by omega. So really this number here affects the period. It affects how large a full cycle is, how long it takes to complete a full cycle. B is sometimes called a phase shift. So this number right here, basically it's a horizontal translation. It's a horizontal shift. And really what it affects is the beginning of the cycle. Okay, now that's why I called it B. Now in the basic sine and cosine functions, there is no B, and B is 0, and that's because the graph begins at 0, right? Here's the cycle, and it begins at 0. But as we'll see moving forward, if you have a graph whose cycle doesn't begin at 0, it begins at something else, then that will determine B. And then finally, M, of course, M is like a number being added on at the end. On the outside of the function, you might remember that that corresponds to a vertical shift of some kind. So M, of course, shifts the whole graph up and down, which changes the location of the midline, this horizontal line going through the graph. So M actually determines the midline, and that's why I call it M, because this is associated with the midline. So now let's move on and do an example. And what I want to do is I just want to write down a generalized sine function. That's a sine function with, you know, lots of different things done to it. And I just want to identify the amplitude and the midline and all those other things. Okay, so here's my generalized sine function. Y is equal to sine 4 times x minus pi over 4 minus 2. Okay, so this is a sine function that has been heavily modified from the original basic parent sine function, and our objective is to determine all of the things that I talked about on the previous pages. What is the amplitude? What is the midline? What is the beginning of the cycle? All that stuff. So let's start by thinking about the amplitude. Well, the amplitude, if you remember, I said is the absolute value of A. Now, if we compare this function with the sort of general template I had a moment ago, let's remember what it was. A sine omega x minus b plus m. That's the general formula. If we compare these two things, we see that A is definitely -3. The amplitude is the absolute value of A, so the amplitude is just 3. You know, what that's telling you is that if you graph this thing and you look at the midline, this distance right here would be 3 units. That's what it's telling you. The angular frequency, of course, is just given by omega, which is clearly 4. Now what that means is the graph completes 4 full cycles in an interval of 2 pi. That's a little hard to imagine and kind of abstract. It's much more concrete if we think about the period, which essentially captures the same information. So what is the period? Well, the period, if you remember, there's this formula, which I sort of circled on the previous page. The period is given by this formula dependent upon omega. Oops, sorry. So it's P equals 2 pi over omega. All right, so if we plug in omega, we find that p is equal to 2 pi over 4, which reduces to pi over 2. So that is the period. What that means is that it takes pi over 2 units of time for the graph to complete a full cycle. In other words, if you look at one complete cycle, okay, of this graph, here's what one complete cycle looks like, then this thing right here will be pi over 2 units long. That's what the period is telling you, okay? What else? We have the phase shift, right? The phase shift, if you remember, is determined by b. So here's b right here. That's the phase shift. So what is the phase shift in this case? Well, it's pi over 4. Now, I mentioned that the phase shift is a horizontal translation, which means it could be to the left or to the right. And the presence of this pi over 4 is really telling you that the graph has been shifted pi over 4 units, but I want to indicate in which direction. Is it pi over 4 units to the left or to the right? Because b is being subtracted here, b is actually equal to pi over 4. This is pi over 4 units to the right. You might remember from last year that horizontal translations are sort of backwards. If you see a minus, then it's actually to the right, and if you see a plus, then it's actually to the left. That's what's going on here. So I mentioned that the phase shift, I call the phase shift b, basically because b stands for the beginning of the cycle. So if you graph one full cycle of this function, here's the beginning, okay? Maybe the beginning starts right here, and maybe the graph looks like this. We'll worry in a moment about exactly what the graph looks like. But if the graph looks like this, the question is, where does this cycle begin? Like, what is this point right here? The answer is b. The answer is pi over 4. Okay, so if you wanted to graph, and we're not going to do that here, but if you wanted to actually graph one full cycle of this function, then you would begin your cycle at pi over 4. Okay, so when I'm talking about the beginning of the cycle, that's what I mean. All right, b is pi over 4. The cycle that you're going to graph, if you were graphing this, would begin at pi over 4. What else? And then there's one more thing that we haven't thought about, and that's m. That's the midline. Okay, so the midline is given by m, which of course, looking at our function, is -2. Okay, so m is -2. And what that means, basically is that, if you've got an xy grid like this right here, then the midline, which is the horizontal line going through the middle of the graph, would actually be sitting at -2. Okay, so whatever the rest of the graph looks like, this is the midline. This is the horizontal line that the graph goes through. So maybe the graph looks something like this or whatever it is, but this line goes through the middle of the graph, okay? All right, so now that we've seen a little bit about how to actually identify each of those characteristics from the formula, I want to move on to one of the big kinds of questions that we're going to be answering here, and that's finding the formula of a trig function from its graph. So, this is something we're going to spend a lot of time on. It's a really important topic. If someone gives you the graph of some trig function, like here's a trig function, how do you find its formula? I just want to point out this graph is obviously not the same as these basic sine or cosine functions. All kinds of things are different about it. It's obviously much taller, for example. And, what's basically happened is that this is either some sine or cosine function, but with all kinds of transformations applied, vertical shifts and everything else. And the key to writing down the formula for this graph is to basically identify the values of all of the numbers that appear in the general sine function formula. In other words, we have to identify a and b and m and everything else. Okay, so let's try to find the formula for the graph that is pictured right here. Okay, now I've got some steps on the worksheet which you should have access to. It says, suppose I give you a sine or cosine graph. To find the formula of the graph, follow these steps. So first of all, you should decide whether to use a sine or cosine function. So here's the thing. What I've done here is I have highlighted one cycle of this graph. Technically, this graph goes on forever, oscillating in both directions, but I've sort of highlighted one complete cycle of this graph, as you can see here, the solid line. With this cycle in mind, we're really going to focus on just this cycle. With this cycle in mind, we have to look at it and ask ourselves, is this a sine or a cosine graph? If you remember what I said about the difference between sine and cosine graphs, the sine function begins in the middle of a wave, whereas the cosine function begins at like a peak. Okay, now if you look here, this cycle is beginning right here. Is that the middle of the wave or is it a peak? Well, it's definitely not the middle of a wave. It's got to be a peak, which is telling me that this cycle is going to be modeled using a cosine function. So this is a cosine function, which means right away that I can write down sort of the general formula, right? Here's the general formula for a cosine function. Y is equal to a cosine omega x minus b plus m. Okay, so that's kind of the general template, and all I have to do to write down the formula is find all the values of these things, a, omega, b, and m. Okay, now in the worksheet, I've said, step 2 is identify the midline m. What horizontal line cuts through the middle of the graph? So where is that midline? You can see it looks like it's right here, right? You can sort of tell that that's cutting right through the middle of the graph, right? Because 3 units up to the top, 3 units down to the bottom, this is the midline, and that's happening at 2, which means that m is actually 2. Okay, so that's m. Next, we should identify the amplitude. If you remember the amplitude, that's the distance from the midline to one of the peaks. So what is this distance right here? Sure looks like that's 3 units. So the amplitude is 3. Now, I want to be careful and emphasize that that does not mean that a is 3. Because remember, the amplitude is the absolute value of a, okay? A could be 3, or it could also be negative 3. Both of those values for a would produce an amplitude for 3. And so what we have to do is ask ourselves, is this graph upside down or not? If it's upside down, that means that a is negative. But if it's right side up, then that means that a is positive. What you need to do is compare your cycle right here, okay, with one cycle of the basic cosine graph. So here is one cycle of the basic cosine graph. Here it is. And as you can see in the parent cosine function, the graph begins at the top of a wave. But my cycle begins at the bottom of a wave. That means that it's upside down compared to the basic cosine function. Therefore, a must actually be negative. That means that a is negative 3. Okay, so a is determined by the amplitude, but then you always have to ask yourself, is the graph upside down compared to the basic cosine graph? What else? We need to identify b, which is where the cycle begins. Okay, now we've highlighted this cycle right here. You can see it's clearly labeled cycle beginning. Where does it begin? At pi over 3. So that's telling me that b is pi over 3. And then there's just one more thing. We need to find omega. Now, omega, of course, represents the angular frequency. That's like the number of full cycles that the graph completes in an interval of 2 pi. Pretty hard to wrap your head around. Instead of thinking about the angular frequency, you should think about the period, and then use that formula, which relates the period in omega, to find omega. So let's think about what the period is. How long does it take to complete a full cycle? Well, here's the beginning of the cycle, here's the end. How long is that interval? Well, if you're not sure, then what you can do is just take the cycle end and subtract the cycle beginning, and that will give you the cycle length. So 5 pi over 6 minus pi over 3. I need common denominators to simplify this. That's 5 pi over 6 minus 2 pi over 6, which gives you 3 pi over 6, which reduces to pi over 2. So that is the length of this cycle, which means that's my period, right? So the period p is pi over 2. Now using this formula, p equals 2 pi over omega, I can find omega. We just agreed that p is pi over 2, so if I plug in pi over 2 into that, I have pi over 2 is equal to 2 pi over omega, and now to solve this equation you can just cross multiply. So if pi times omega is pi omega, and then 2 times 2 pi is 4 pi, you want to solve for omega, so just divide both sides by pi, and you get omega is equal to 4. Okay, so we now know everything that we need to know, right? We've identified all of these values. Now you just plug them in, and you've got your formula. So I guess it's going to be y equals negative 3 cosine 4 x minus pi over 3 plus 2. And that's the formula for this function.